everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about the common ion effect and applying it to solubility. So one of the cool things that we may have already noticed is that it turns out that when we're trying to dissolve a compound in water, most of the time we're never going to be using pure distilled water. Most of the time we're using things like tap water, and even distilled water can have a lot of impurities in it, like calcium, chloride, carbonates, nitrates, ammonia. There's a whole variety of compounds, and each of these can have an impact on solubility. And so this will end up affecting the solubility of all of our various ionic solids. So a good way to look at this is, imagine I'm trying to dissolve my fluoride. So calcium fluoride goes to calcium and fluoride. However, it turns out that here in the Midwest, almost all of our water is going to have a lot of calcium in it. So if I'm trying to add the fluorine, I run into this issue. If there's already calcium present, that's going to push the reaction to the left. And so the question is, how much is this going to affect the solubility of our calcium fluoride? Well, one of the things we can do is actually kind of quantify this. So we can generate an ice table by assuming that the concentration of calcium is 1.5 millimolar. So by doing this, what we can do is construct our typical ice table. But the big difference here is that our initial concentration of calcium is going to be 1.5 millimolar, which, it is worth noting, is fairly above the level of calcium produced by the normal calcium fluoride dissolution. So as a result, we should be able to neglect our X here when we're calculating our KSP. So we're going to go ahead and just treat the concentration of calcium as being relatively fixed at 1.5 millimolar. In truth, there will be generation of slightly more calcium, but the level should be so low that this number won't really change. And we'll go ahead and double check that in a bit. So when I do this, I can then plug in these two concentrations into our equilibrium constant, and it turns out that we're going to have a little bit different of an equilibrium constant we had before, because now the KSP is equal to a number times x squared instead of x to the third in the normal equation. However, that will actually make the system a little bit easier to solve, as I then try and calculate my solubility, which again should be the same as x, will be simply the square root of the KSP divided by this 6 times 10 to the third number. And here we find out that our x value is about 6.5 times 10 to the negative fifth. And it is worth noting that this will come in just under affecting the sig figs of our calcium concentration. So it actually is fairly okay to neglect the influence of x here. However, what that means is that the solubility of calcium fluoride under these circumstances is about 5.1 milligrams per liter. This is actually really interesting because in pure water, it has a solubility of almost 3 times that amount, of almost 15 milligrams per liter. And so what we found is that by changing your water source, you actually really change the solubility of our fluoride. So if you're going to be fluoridating the nation's water, you're going to want to pay attention to what the purity of that water already is. Doesn't contain calcium. That will change the amount of fluoride you're going to want to put in. And it can be very useful. These solubility effects can be useful in these natural kind of experiments, but also using the common ion effect can be very useful in trying to reduce the solubility of often very common and toxic substances. So one good example is called calomel. This is also known as mercury chloride. So it turned out that calomel really once used to be the cure-all of all medicines. It would cure anything from fungal infections to syphilis. Unfortunately, you may notice part of the problem here. It was hard to tell whether the patients were going mad from the syphilis or mad from the mercury poisoning, because calomel is quite toxic. And because it was used so widely in scientific equipment and in a lot of medicines, there's still a fair bit of it out there in the environment. So one of the questions is, how can you reduce the solubility of the calomel? So let's go ahead and first take a look of trying to figure out, well, how much calomel will actually break apart normally. So if I put calomel into pure water, the ice table looks almost exactly what we had for fluoride. One component breaks apart into 3. So the KSP will be very similar, have the form of 4 times x cubed. We can then solve for x, which will be about 7 times 10 to the negative 7th molar. Or once you include in mass, it comes in at about 0.3 milligrams per liter. So it is worth noting this is an insoluble substance. It is fairly low, not much of it. We wouldn't expect much of it to break apart in water. However, there is a problem when you're releasing that much mercury into the environment. This is still quite toxic levels of mercury, way above any sort of safe levels. So how could I go ahead and impede the dissolution of this mercury chloride in water? Well, we're not going to want to add mercury because that would be bad and would defeat the point. But what would happen if I added chloride to the system? I could use the common effect to increase the amount of chloride, which should push the reaction to the left, meaning less of the mercury chloride would break apart. Now let's go ahead and test this by looking at the solubility. So what would happen if I added the calomel to a 0.1 molar sodium chloride solution instead of pure water? Well, in this case, my chloride ions would be at 0.1 molar, so we can generate an ice table for that. Initial concentration of chloride is 0.1 molar. Again, I'll be producing some mercury and some chloride, but as we saw before, the chloride concentrations that we're going to be producing are going to be on the order of 10 to the negative 7th. So it's going to be very safe to assume that X is sufficiently small here, so I can treat the chloride concentration as just 0.1 molar. So then I can plug this into our equilibrium constant. So mercury is just going to be X, chloride is just going to be 0.1 molar. So it turns out that my KSP would then be equal to 0.001 times my solubility. So I can then solve for X and thus the solubility by just dividing KSP by that 0.001. Which turns out that this drops my solubility times 1.2 times 10 to the negative 16th molar. So that's quite a low solubility. And even when we convert it to a mass solubility, it's on the order of 7 times 10 to the negative 15th grams, or 7 femtograms per liter. So it is worth noting the mercury will still be breaking apart, because it turns out to a certain extent everything is soluble and will always break apart. But at this point, by most standards, this would be considered a fairly safe level of ambient mercury. So if you're dealing with substances that can be quite toxic, such as mercury or lead, one of the things you can do is try and find what common ion effect will essentially drive the system back into solution, preventing it from breaking apart. And this is a very good lesson in both medicine and in environmental toxicology. So next time, we're going to go ahead and take our knowledge of solubility and talk about acid base. What?